Так, до сих пор я и вот и ум остался здесь. Отключим пока ум.
Отключим.
Все, кто хочет увидеть это все в YouTube, я в следующий раз просто пишу письмо всем, кому рассылается. Если
Я прошу прощения, там
то
ничего не сломается сейчас, если трансляция, ой, в смысле зум будет.
Нет, зум не должен. Давайте опробуем, ладно. Все, короче, опробовать надо.
А в зуме там никого нет, да?
А никого кроме меня. Вот видите, зум, презентация завершена. Организация. Все.
А микрофон нужен?
Он будет только.
А, запись, да, будет?
Это просто трансляция на YouTube.
А включено, да? Нормально?
По идее,
Не, да, там видно.
Как проверить?
да, здесь. А свет вам нужен? Могу лучше ставить.
А можно он там выключить сзади? Вот хотя бы так. Не, вот это вот людям нужен. Ага. Спасибо. Так, начинать?
Да.
So, I speak English. So, thank you for invitation for the seminar. So, my talk is about Manin matrices and quantum representations, which can be described via these Manin matrices. So, okay. The plan of my talk is following. First, I briefly review the subject of Manin matrices. Then I introduce some notion of in the algebraic geometry, and I introduce action of classical groups and how it can be, how we can consider non-commutative case of the actions. So this is actions of quantum groups on quantum spaces. This is well-known thing. It's usually called commodule algebras, but my aim is to construct, this is some non-commutative version of non-linear actions, and my aim is to consider linear actions. So I need quantum analog of linear spaces, and so next I explain what is quadratic algebra and why quadratic algebra can be considered as quantum linear spaces. So then I introduce generalization of Manin matrices for general quadratic algebras. And там нет, там компьютер туда. Okay. So then I introduce quantum representations and explain how to describe them via these general Manin matrices. As example, I consider first classical representation of finite dimensional algebras. I consider classical representations as quantum representations. And then I consider Manin matrix algebra. It has action on the vector space, and I present the quantization of this action this is no known quantization, but usually people describe it in terms of non-linear actions, in terms of comodular algebras. So, but it can be described as quantum representations. Then I introduce quantum representations of quantum groups as a particular case of general quantum representations. As example, consider classical representations of groups, and I consider Manin matrices related with Yangians, and I extend this Yangian, and this extended Yangian has a quantum representation. So first of all, I need some conventions. As a basic field, I take some arbitrary field of characteristic 0 denoted by k. All vector spaces are over k. Tensor products is also over k, just denoted by this symbol. By algebra, I will mean associative algebra over k, which has unity. Graded algebra is in this sense, which has structure of n-not grading, where n-not is the monoid of natural numbers with 0. So it looks like this. Then if we have an algebra, not non-graded algebra R, and graded algebra A, so we can consider product of these algebras just because if you have two algebras, we have tensor product of these algebras. And if one of these algebra is graded, we can define grading on the tensor product in this way. Then consider the polynomial algebra, which consists of polynomials of two variables. This is a graded algebra generated by two commuting elements x and y of degree 1. More generally, we can consider algebra of polynomials over an arbitrary algebra R. In this algebra can be considered as a tensor product of non-graded algebra R and graded algebra of polynomials. So it defined by the formula 2, general formula 2. So it means that the degrees of the elements of the algebra R are 0. Now consider graded homomorphisms from between these two polynomial algebras. It always has the form written here. So write it in matrix form. It has this form because this is graded homomorphism, so it should respect grading. And so the images of x and y should be linear combinations of x and y with coefficients in R, which I denoted by A, B, C, D. And we can write it in this matrix form. And to have really homomorphisms, we need the condition that the images of x and y commute with each other. And this condition is equivalent to these three relations 4.
I'm sorry, was this condition that f of x and f of y commute
because the algebra R of x and y, this is algebra over R with relation that x and y commutes. And also the algebra over K also x and y commutes. So if we want homomorphisms, okay. So if we denote this algebra ABCD by M, so this is 2 times 2 matrix M, it is called Manin matrix if it satisfies these 3 relations for. It means that entries in columns commute with each other, and additionally we have some relation which is called cross relation.
The third relation is the cross relation.
Yes.
Is it really necessary to provide the commutativity?
Huh?
So all 3 relations are equivalent to the homomorphicity of F.
Yes, yes.
Okay.
Then Manin considered question.
Sorry, you have question?
No. So Manin considered such matrices in a Q-deformed case, and the term Manin matrix appeared in the paper of Cherlov and Falke, and they also defined notion of Manin matrix for any rectangular matrix, a matrix of size n times m. So if M is some matrix with entries Mij, where upper index j is index of row, lower index, upper index I is the index of row, lower index j is the index of column, this entries belongs to some algebra R, and this is a Manin matrix if it satisfies these relations. And again we have commutativity, relations 5 are commutativity in the same column, and 6 is the cross relations for the matrix for 2 times 2 submatrix according to the indices I, J, K, L and L. Yes, so by these relations are exactly the relations for. You can write it as commutators. It means that rectangular matrix is a Manin matrix if and only if any 2 times 2 submatrix of this matrix is a Manin matrix. And again, there is one-to-one correspondence between Manin matrices over R and graded homomorphisms between the polynomial algebras. For the Manin matrix M, this homomorphism is given by the formula 7. Note also that if we have a commutative algebra R, then the matrix over this commutative algebra is always a Manin matrix, because the entries of this matrix are pairwise commuting. Or more generally, R could be non-commutative, but in non-commutative entries could be commutative, pairwise commutative. But this is stronger. Huh? So the pairwise commutativity of entries is more general condition. So the matrix satisfies this condition if and only if M and it's transposed are both main matrices. Then, if we have two main matrices of the same size, we can consider the sum, but it is not always main matrix. It is main matrix if entries of M commutes with entries of M. And the similar for product. If we have two main matrices, maybe of different size, but such that we can define product. And again, if entries of M commutes with entries of N, then the product is also a main matrix. So as we know, any 2 times 2 submatrix of main matrix is also main matrix. But in fact, any submatrix of this matrix, of a main matrix, is a main matrix. Then if we permute rows or columns of the main matrix, we obtain a main matrix again. Or we can double rows and columns, increasing size of matrix. Or we can substitute one row instead of another row, or one column instead of another column. In this way, we obtain a main matrix from a main matrix. If M is invertible square main matrix, then its inverse is also main matrix. And this is some basic properties, and there is many others facts which can be considered as generalizations of facts from classical matrix theory. And there is many facts found in paper of Chervov, Falke, and Rubtsov, like Kramer's formula. So this Lagrange, Desano, Jacobi, Carroll formula. By Carroll, I mean Lewis Carroll. And Jacobi's ratio theorem, Sylvester's determinant identity, Kashibina formula, Capelli type identities, Kelly-Hamilton theorem, Newton identities, and McMahon-Vronsky relations, and others. And many matrices have a lot of applications. So in the first paper, Chervov and Falke, where they introduced the notion of main matrix, they applied main matrices to the XXX model, to the Talalayev's formula for the Godin model, to the Knyzhnik-Zamolodchikov equation, the separation of variables, and to the center of affine Lie algebras. Then there is applications to higher Sugawara operators and to elliptic Godin models. And there is many generalizations. So Manin himself considered some case with multiparametric deformation. And he considered this case a super case. And it was a paper even before Chervov and Falke about McMahon-Marsa theorem for the Q case. So we call these matrices Q-main matrices. And they call them right quantum matrices. Also, Isaev and Agevetsky considered some kind of generalization of many matrices, which can be defined by using our matrices of Hecke type, which satisfies Hecke relations. And they obtained Kelly-Hamilton-Newton identities for these matrices. For super case, so-called super many matrices, Wolff and Ragusi found generalized McMahon-Masser theorem and considered higher Sugawara operators. Then Wolff in his book defined Manin matrices of types B, C, D and applied them to higher Sugawara operators. And in this work I considered Manin matrices in some general sense for the arbitrary quadratic algebras. And then I defined some quantum representations in the next paper. And these representations can be described by these general Manin matrices. So today I explain what is it. So first of all, I remind some notions from algebraic geometry. So instead of some varieties, manifolds, I consider algebraic sets, or so-called affine algebraic sets, which I just call algebraic set. This is a set of solutions of the system of polynomial equations. They're defined by a set of polynomial functions f alpha. We have R functions, and in particular if R is 0, so we have no relations, then all the points are solutions. So n-dimensional space is also an algebraic set, and if we consider it as an algebraic set, we denote it by an and call it affine space. This is not the same as linear space because we have different morphisms. We have not only linear morphisms as for linear spaces, but we have more morphisms. Morphism between affine spaces is a map of this form, where pi's are polynomial functions. We also call these maps regular. And more generally, we define a regular map between two algebraic sets x and y, which are defined as subsets of affine sets an and am. And the map between this algebraic set is called regular if it's induced by a regular map between these affine spaces. It means that the diagram 9 is commutative. Okay.
So phi is just restriction of capital phi.
Yeah.
And you don't have any definition otherwise than that. So just you always have some ambient. You always have a morphism of ambient space, and the only question is what it does with subset, right? There is no intrinsic definition of map of affine sets, affine algebraic sets. Am I right? You cannot define a map of affine algebraic set without referring to the map of algebraic affine spaces, right? Okay, let me say it faster.
No, maybe we can, but this is the easiest.
Выражение из x в y, которое не затрагивало бы это выражение объемлющего пространства. Или оно не существует, или просто вы не хотите сейчас его давать?
Наверное, существует.
Нет, я просто хотел...
Но через алгебру?
Понять,
So the best way is to use algebras of functions to define it.
Yeah.
Yeah, but this is in the next slide. So no, first of all, we need to define regular maps anyway. So to define algebra of functions. So the regular maps are two regular maps from affine set X to the one-dimensional space A from some commutative algebra. It is denoted by A of X and called algebra of functions. In particular, if X is a affine space, then the algebra of functions is the algebra of polynomials. And there is famous fact from algebraic geometry that there is one-to-one correspondence between regular maps between algebraic sets and algebra homomorphisms between the corresponding algebras of functions, but in the reversed order. And because of this fact, we can interpret algebras as some non-commutative version of affine sets. So let us call it non-commutative space or quantum space. So quantums, but to call quantum space. Quantum spaces are arbitrary algebras with reversed morphisms. In terms of category theory, it means that a quantum space is an object of the category dual to the category of algebras. No, dual, or sometimes people call opposite category. Now we need definition of bialgebra. Bialgebra is an algebra R equipped with two algebra morphisms called multiplication and co-unit, which satisfies the condition that these diagrams are commutative. The first diagram, the commutation of the first diagram is the condition which is called co-associativity. And the first one means that co-unit is a co-unit for this multiplication. A Hopf algebra is a particular case of bialgebra. This is a bialgebra with the condition that there exists a linear map zeta called antipode satisfying this condition. So this condition is defined via the co-multiplication, co-unit, the multiplication map mu r, which is defined in this way, and mu r defined in this way via the unity of r. A fine algebraic monoid is an algebraic set equipped with the structure of a monoid such that the multiplication map defined in this way is a regular map of algebraic sets.
So what is regular? Regular is just something given by polynomials on the environment,
Yes.
ambient affine space, right?
We have some affine coordinates.
Yeah. So regular is anything given by polynomials and coordinates, okay?
Yeah. So if we have a fine algebraic monoid, then this map, which is regular, induces a co-multiplication on the algebra of functions.
how to define the algebra functions as just affine maps with values in affine line,
This is
right?
polynomial maps.
The values in affine line, anything with values in affine
Yeah.
line. So is it difficult to show that in fact the tensor product of AG with AG is equal to AG cross G? Or is it something given by definition?
So
This isomorphism between AG
yeah, sometimes
of tensor
it's given by
product
definition.
and this functions. It actually in analysis, this is something totally non-trivial. I would say you need to pass the completions on the left of the tensor product, and you might not take any completion. You need to
Yeah.
do it carefully.
So why I consider just an algebraic version?
And in algebraic version, you always have this isomorphism. Because I'm not familiar with algebraic geometry, so I just wonder whether there is any, so to say, any difficulty, any tricks or any conditions that should be satisfied. So we have this isomorphism.
So in algebraic geometry is always.
This is always the case.
Yeah.
That's right.
Yeah, but
So scheme theory.
I think maybe you should set certain conditions on the field,
Yeah.
like algebraically closing.
That's what I thought when I read
Yes, I mean
Uh,
not algebraically closed field.
And also you need to make sure that this map is
So in the scheme theory, you can consider non-algebraic field, and this is just a definition in the scheme theory.
Well, I mean, this difficulties appears when we consider algebraic varieties. That means that we apply extra conditions on algebraic sets. They should be reducible. Then this means that these algebra functions is an integral domain. And then when we take the tensor product of a non-algebraically closed field, it can happen that this ring will be will have zero divisors. But the product of varieties, the regular operation, this is again an algebraic variety if the field is algebraically closed. But you can take for general field, take this as a definition, say.
What definition?
I mean,
the product is.
that A of G cross G is
Oh,
just
yeah. I see. So it's just since the definition of G cross G was not given,
yes.
we can actually just put
Yes.
by
We
definition.
can define like this, but we can prove that
I see.
this product can be embedded to some.
Yeah.
No, I mean,
Affine
that
spaces.
there are certain difficulties with algebraically closeness of the field, because otherwise some properties will lose. For example, if you consider algebraic varieties, then you probably will need that the product is also algebraic variety, and then this tensor product of a non-algebraically closed field can have some problem. But okay,
So
skip.
yeah, but today I consider some general theory.
I just wonder whether there is any.
It doesn't matter. Is it integral? Or not
No, I understand, but I suppose that we will develop this theory in full generality, consider these categories of algebraic sets and blah, 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 then probably certain properties
Should be satisfied.
Yes.
That's precisely what I was worrying. Okay, next time.
For algebraically closed field, there are no problem at all.
There should be one. I believe you.
okay, then. So we have co-multiplication on the algebra function, and also we have co-unit defined via neutral element of the group. So algebra functions become commutative by algebra, and morphism of affine algebraic monoids correspond to the bialgebra homomorphisms in the reverse direction. And affine algebraic group is a particular case of affine algebraic monoid. This is a affine algebraic monoid, which is a group in the set theoretical sense, and this map is a regular map from G to G. In this case, the algebra function is a commutative Hopf algebra. So, and Drinfeld defined quantum groups as arbitrary Hopf algebras with reversed morphisms. So in terms of category theory, it means that the quantum group is an object of the category opposite to the category of Hopf algebras. And more generally, we can define quantum monoids as arbitrary algebras with reversed morphisms. And so we have quantum space. Quantum space is an algebra, and multiplication and counit is the structure of group. They give a structure of group on the quantum space. But we cannot call it non-commutative group, because non-commutative group is just a group with non-commutative multiplication. So what's so Drinfeld called it quantum group. So quantum is something dual to the non-commutative. Then let me remind what is an action, also called left action. We have an affine algebraic group G and algebraic set X. An action of G on X is this regular map satisfying these conditions. And now, what is the quantum version of the action? In this case, we have quantum group instead of G. The quantum group is Hopf algebra H. Or more generally, it can be a quantum monoid, that is a bialgebra H. So instead of X, we take quantum space. The quantum space is an algebra R, and the quantum analog of action is these homomorphisms of algebras. And the condition is that this diagrams commute. So in the classical case, instead of by H, we need to take bialgebral functions of G on G, and R will be an algebral functions of X. And this is a correction in the monoidal category of algebras with the tensor product. And there is also a notion of commodule algebra. Commodule algebra is a pair of the algebra R with the correction delta. So this is a quantum version of this nonlinear action. Because we don't have requirement of linearity, and we even sometimes do not have linear structure on X. So if instead of X as X, we can take affine space. Affine space is, as I said, is a linear space, so we can require linearity in this sense. And this is actually, in categorical sense, this is an additional structure. And we know the theory of actions and the theory of linear representations are different theories. So we cannot so the same should be for quantum case. So we have quantum actions as commodule algebras, And for quantum linear representations, which are called quantum representations, we first need to define quantum linear space. So quantum linear spaces is quadratic algebras. So first I define quadratic algebras. This quadratic algebra is a graded algebra generated by some number of elements. We will consider only finitely generated quadratic algebras. So we have finitely many generators, and the commutation relations have this form. So this is the quadratic commutation relations. We have n square monomials, xi and j. So we have maximum n square independent relations. But we can add dependent relations here and to make r equal to n square.
So these are non-commutative variables, x1 for xn.
Yes, yes.
And you take polynomials over k, non-commutative polynomials over k.
Yes, because all the algebras are over k. And here, coefficients belongs to k. So instead of alpha, I can take two pairs of indices from 1 to n. So I can write 11 as 12. I just add dependent relations if I need. And the proposition is that for any quadratic algebra, I can write commutation relations in terms of some matrix. The matrix A of the with entries. I take these coefficients, and these coefficients can be considered as entries of the matrix A. And this is n times n square times n square matrix. And the statement is I can always take I can always choose idempotent matrix A. That means that A square equal to A. And I will use this notation if we
So how do you define A square? It's n square by n square matrix. So we just take product, just A, can you write down a formula for the product of matrices in this coordinates and this indices?
So the PQ, for example, and some PQ. It should be equal to A, K, P, I, J. Okay. And for idempotent A, I will use the notation xa of k. This is a quadratic algebra defined by these relations. Okay. So consider polynomial algebra. This is a quadratic algebra with commutation relations that xi and xj commute. This is quadratic commutation relations. So the polynomial algebra is the quadratic algebra for the idempotent in AN. AN is just an antisymmetrizer of two n-dimensional vector spaces. It can be defined by the formula 14, where Pn is the permutation operator. V and W are vectors from Kn. Okay. Now consider n-dimensional vector space as an algebraic set. So this is algebraic set AN, the n-dimensional affine space. Now consider regular maps between affine spaces of different dimension, maybe. In these regular maps bijectically correspond to the algebral homomorphisms between polynomial algebras. And here we have all homomorphisms, not only graded. But we can ask when this regular map is a linear, because we know as a set, affine space is just a linear space of the same dimension. So this regular map is linear if and only if the corresponding homomorphisms is graded. So as we discussed, we considered affine sets in terms of algebra functions. So in the same way, we can consider linear spaces in terms of its algebra functions, but the additional structure on linear space, the linear structure, this is corresponds to the grading on the algebra functions. So if we have vector space V n-dimensional, so we have algebra functions of n variables, and it should be graded algebra to describe the linear structure. And we can write it as symmetric algebra of the dual space, because dual space consists of the linear functions on the space V, and all the polynomial functions on V form the symmetric algebra of this dual space. Okay. So we can define quantum linear spaces as quadratic algebras with the reverse morphisms. So quantum linear space is an object of opposite category to the category of quadratic algebras. We could consider some more a bigger category, but let it first be just quadratic algebras. So the simplest example of the quadratic algebra is the tensor algebra of fine-dimensional vector space. This is a quadratic algebra with n relations, with n generators and no relations. So the corresponding idempotent is 0. So the tensor algebra of V is quadratic algebra for the idempotent 0. There is also famous Grassmann algebra. This is also example of the quadratic algebra. It defined as quadratic algebra generated by n variables, which should be anti-commuting. In particular, the squares are 0. And this is a quadratic algebra for the symmetrizer. And we can also consider a deformation of the polynomial algebra. So we can have many parameters of deformation. So let Q be a matrix of these parameters. So this square matrix, the entries are non-zero elements of K. They should satisfy the condition that Qij is inverse to Qji, and Qi in the diagonal should be unities. And we can define the quadratic algebra using these deformed computational relations. And this is quadratic algebra for this idempotent. As a quantum linear space, it is multiparametric deformation of the n-dimensional vector space. In the case of dimension 2, we have only one parameter, denoted by just Q. So this matrix of parameters have this form, and we have one relation that the variables generators of the algebra, x1 is x, s2 is y, they should be Q commutative. And this relation defines quadratic algebra, which we denote in this way. We call it quantum plane or Q plane. This is quadratic algebra for the idempotent AQ, where this AQ is this AQ for this matrix.
Just a moment. I want to write down this relation.
Which relation?
Thanks.
Now I introduce general matrices. Let us consider two quadratic algebras for two idempotents A and B. They can be of different sizes. The generators of these algebras are denoted by xia and xjb. In terms of these generators, I can write graded homomorphisms of these graded algebras. From the quadratic algebra for A and this tensor product, where R is an algebra. So any such graded homomorphisms have this form, where the coefficients are elements of the algebra R, and the matrix of these coefficients should satisfy the relation 16, where we use the standard notation, tensor notations. So we can and my definition is that a matrix satisfying this condition is called Manin matrix for the pair of idempotents A and B, or I will just call it simply AB Manin matrix.
Just a moment, don't.
Yes, and this statement means that the set of AB Manin matrices over R is bijective to the set of homomorphisms, graded homomorphisms. It is written as a home set in the category of graded algebras. In the case when these idempotents are equal to each other, then we say B minus matrix instead of BB minus matrix. I need to define some monoidal products in the category of graded algebras. So consider two graded algebras A and B. And the usual tensor product of these algebras is the tensor product as algebras, and it has this natural grading. But we have another product. For quadratic algebras it was introduced by Manin, but it can be written for any pair of graded algebras. So we define Manin product as the direct sum of these components. So here we can, has degree k. Here we have, so in this sense this is degree 2k, but in the Manin product this is elements of degree k. And we can embed this algebra to this algebra, but this embedding is non-graded homomorphisms of algebras. And if we take quadratic algebras A and B, then zero components are just a field K. So if we consider the component of the products of the degree 1, it will be a direct sum and direct product. For the usual tensor product, this is direct sum, and for the Manin product is the tensor product. So if we have a quantum linear space that is a quadratic algebra, then the classical part of this quantum linear space is the vector space, which is dual to first component of this quadratic algebra. So from this formula we see that the product these tensor products and Manin product of quantum linear spaces are analogs of the direct sum and tensor product of vector spaces. So in particular, if we want the role of tensor product for quantum vector spaces is played by Manin product. We have a functor which embeds finite dimensional vector spaces into the category of quantum vector spaces. It takes a finite dimensional vector space V and maps it to the symmetric algebra of its dual. And this functor weakly relates the tensor product of vector spaces with the Manin product. Weakly means that here we have not the morphism, but just a morphism in this direction. But even the existence of these morphisms, it should be natural in the categorical sense. This natural morphism allows us to embed quantum representations into the classical representations into the category of quantum. So to define quantum representations, we need this algebra, denoted by UAB, a quadratic algebra generated by these elements. And the computation relations is written via the matrix of, we can consider these elements and as entries of this matrix, and we define this algebra by this computation relation. This computation relations is exactly the definition of Manin matrices, AB Manin matrices. So it means that M is AB Manin matrix, and I call it universal AB Manin matrix because other AB Manin matrices are homomorphic images of the universal AB Manin matrix.
So this is again algebra over K.
Huh?
So this algebra is also over K.
Yes. There is a proposition that there exists natural isomorphisms. Natural bijection between these two sets. This is sets of graded morphisms between from quadratic algebra to this graded algebra, because we take C as graded algebra, general graded algebra, and XB is another quadratic algebra. So here U and B is the algebra which we define by the relations 19, and we have graded morphisms to the graded algebra C. We have this bijection. This statement in the case of quadratic algebra C was obtained by Manin, but we need more general statement for arbitrary graded algebra.
Could you please
Huh?
write again like what the relations for this UAP? Quadratic algebra is generated by Mij. This means that it is generated by
So PQ and ST, for example. ST, IG. So this is a unit matrix. Centers are delta SI, delta C.
Yeah, I mean the algebra UAB itself.
Yeah.
How it's defined here? You mean that it has generators x1, xn, x1, xn?
No, generators are M. M itself are generators. We have n M generators. Okay.
But then, what is even for this quadratic algebra? It's the product of A and 1
Yeah.
plus B.
Hard to say.
Do you have to, it's not so.
So yeah, can calculate it, but not in 5 minutes.
Okay. Well, maybe there is some simple formula.
I don't know.
Для меня неизвестно.
Okay, so next. Yeah, so we want to define quantum representations. So what we want to represent? So in classical case we represent groups and algebras, maybe something else. In this case we represent quantum algebras. No, I call this thing, these objects as quantum algebras. Yeah, so define quantum algebra as a graded algebra A equipped with the graded homomorphisms delta and epsilon. And I use here Manin product.
Why do you take K of U?
Because K of U is a unit object in the category of graded algebra with Manin product. So we need K of U here. No, K of U is the algebra of one variable.
Just K in every dimension, that's all.
Hmm.
Just K in every dimension, as far as I can understand.
Yes, yes.
With the unique product, which is really, I don't think it's necessary.
And it should satisfy these conditions of commutativity of these diagrams. And this means exactly in terms of theory of monoidal algebras, monoidal categories, it means that quantum algebra is a commanoid in the category of graded algebra with Manin product. But we can describe it in terms of bialgebras, but not just bialgebras, but some bialgebras with grading. And how we can do it? We can embed this. No, we have this embedding. Embedding is not graded, but we can compose it with these graded homomorphisms delta, and we obtain this map, which I denote by delta A. And for epsilon, I take its composition with the evaluation in U equal to 1. So I obtain a map epsilon A. And these maps, delta A and epsilon A, are co-multiplication and co-unit for the algebra A. So we have a bialgebra, but this is not graded bialgebra. Conversely, a bialgebra, non-graded, defines a quantum algebra if A is equipped with grading such that this condition holds. So if we have this condition, we can define that delta for Manin product.
Bialgebra, but not graded bialgebra, right?
It's not a graded bialgebra. So this is graded algebra, but not graded coalgebra.
Okay.
This is because we use Manin product, not usual tensor product. For algebra structure, we use usual tensor product. For cost structure, we use Manin product. Yeah. So consider a quadratic algebra B for the idempotent B. Then we have that quadratic algebra in the blackboard. UBB is generated by the universal B-Manin matrix M, and this quadratic algebra, as graded algebra, has a structure of quantum algebra, and we denote this quantum algebra as quotient of B. This is a quadratic algebra UBB equipped with this co-multiplication and co-unit defined by the formula 21. And now we can define quantum representation of the quantum algebra A on a quantum linear space B, which is that quadratic algebra, is a graded homomorphism of bialgebras. So this is quantum algebras. We can consider it as bialgebras. So this homomorphism should be a homomorphism of bialgebras, and it should respect gradings.
So just when you repeat this universal algebra UBB with this map, is it just again a homomorphism? Does it give the co-algebra structure, this co-multiplication? Quotient of B. Take quotient of B. So UBB is an algebra.
No, algebra structure, but not graded algebra.
So we have UBB is an algebra, right?
Yeah.
So when you add these two structures, the co-unit and the coproduct, does it become bialgebra?
Yes.
But not graded bialgebra?
Yes.
Okay, but I don't see how you prove that this is a...
Because this is has degree 1,
No, I don't care about
degree 1, and degree 1.
Okay, I don't
So in the usual sense, it has degree 2.
I don't care about degree for a while. I just care about the co-associativity and the...
Yes, of course. Yes.
Map is...
It will be bialgebra. Yes.
Matches with the product. You know, I mean, you need to check that this coproduct should commute with the product. I don't see how this. Okay.
So we
shouldn't skip. Okay.
So we have a structure of bialgebra.
Okay.
Okay. Or some question.
So what do you call graded homomorphism of bialgebras in this case?
Graded. It is graded,
no, but
and this is homomorphism of bialgebras.
B is not a graded bialgebra.
Yeah.
So should it be just a graded map of algebras?
Yeah. So
Should also commute with co-algebras. Oh, you mean
no, this is morphism of commanoid. It's just
in this.
there is general theory of this.
In this model, in this model.
Yeah. Yes.
Okay then. They didn't mention this.
Okay. Then, no, as in classical theory, we have presentations and actions. No, actions define the structure of module on the vector space. So we have some correspondence there, and also here we have bijection. So that is a consider. There's natural isomorphisms for if A equal to B, we have this bijection, also natural. And not natural, because here B are the same. So it's extra natural. And this bijection gives one-to-one correspondence between quantum representations and coactions in the category of graded algebra with the Manin product. Now on this fixed quadratic algebra B.
So on the right you have homomorphism of coalgebras or bialgebras. UB beta A.
No, coaction is from in the left.
No,
Yeah, in the right morphism of bialgebras.
homomorphism
So quantum representations.
of bialgebras.
So the delta in the
Both
from the
product
left.
and coproduct and unit and counit should be preserved by this man.
Yes.
Okay.
So there should be written Koyan to B.
Hmm?
There should be written Koyan.
Yeah, more or less that's
instead
what I
of
would
2B.
expect. But okay, never mind.
Yes, beta. Yes.
Hmm?
Yeah,
Ah.
O and B rather than UBB.
No, this is homomorphisms of
That's what I asked. Is it
no. This
just homomorphism of
You-
algebras?
in this formula it's not. We have all the homomorphisms without structure of coalgebra
So this is just homomorphism
Oh.
of algebras.
of graded algebras.
Of graded algebras.
Yes.
Okay then. So what was
So
the purpose of-
omega form subset here,
Okay.
and
So
and delta form subsets here. No, because we already have these homomorphisms, all these bijection, and we have subsets in this bijection.
So you claim
So-
that the coend these subsets of omegas inside UB to A correspond in one-to-one way with what? With maps from B to A circle B,
Yeah.
right?
So the image of this isomorphism to this direction give the coaction. So coaction is the image of some.
It has definition of coaction. Oh no, it is
No, you
coaction in the
can
sense of
you
that
can
monoidal-
consider as
of that
definition.
monoidal category,
But-
right?
Yeah, but
It's
there is a
correct.
categorical definition.
Okay, so there is
Oh.
this one-to-one correspondence with maps 22, and the correction in the sense of monoidal category with respect to the circle, right?
Yeah.
Okay. Okay, let's go on.
Okay. So, and we can, no, this is an abstract definition of the quantum representations. We can describe it by Manin matrices. But we have, for Manin condition that matrix is Manin, we also need condition that it is multiplicative. What is multiplicative was defined by Manin. A square matrix over a bialgebra R is called multiplicative if its
coproduct is given by this formula, right?
yes, and
Coproduct
counit.
It's the straightforward generalization of group-like elements, right? In the
Mm.
case of matrices.
Yes. And the statement that a quantum representation omega of a quantum algebra A on quadratic algebra B has this form for a multiplicative B Manin matrix M over the bialgebra A with this condition of the degree 1. So we have universal, here we have generators, here generators are entries of the universal B Manin matrix. So this is graded, omega should be graded, so M ij should be of degree 1. it should be a homomorphism of algebras. So we need to condition that M is B-mining matrix, and the omega should respect delta and epsilon, so it should be multiplicative. And conversely, any such matrix defines a quantum representation of the quantum algebra A on the quadratic algebra B by the formula 24. So we have one-to-one correspondence between quantum representations and multiplicative B-mining matrices with the condition of degree 1.
Okay.
So then how to embed classical representations to quantum? So to consider classical representation of a finite dimensional algebra, we take a finite dimensional algebra R, and we can construct quantum algebra in this way. The multiplication of the algebra mu R induces a linear map on the dual space. And we can extend it to the graded algebra homomorphism of the symmetric algebra, such that delta 1 is the first component of delta. And this symmetric algebra is equipped with the structure of quantum algebra because delta is given there, and also we have epsilon k-unit.
Okay.
It is induced by the unity map eta. Then let V be a finite dimensional vector space with some basis, and consider representation ρ of the finite dimensional algebra R on this space. It has this form. So on basis it has by these matrices. So A is an element of R. So for each element we have this matrix. So rho ij can be considered as linear function on R. So this is an element of the symmetric algebra of degree 1. And the condition that representation is homomorphisms is equivalent to the multiplicativity condition for the matrix M with entries rho ij. This is a matrix multiplicative matrix over a symmetric algebra SR star. And M is a main matrix because CR star is commutative. If we have matrix over commutative algebra, it is a main matrix.
Automatically, right?
Huh?
Automatically, because it's commutative.
Yes, yes.
Okay, so this way we turn the functor, leads to the classical representation.
Yeah, and here the representations, quantum representation space is polynomial algebra.
Okay.
So many matrices are matrices for polynomial algebras.
Okay.
So we have a multiplicative mining matrix M. It defines quantum representation.
Mm-hmm.
We have condition of degree 1. And in this way, the functor S star lifts classical representation rho to the quantum level means that we have category of classical representations, category of quantum representations, and the first embeds to the second, and the image of rho is omega. So the example, we can consider this example. Let for R, for this R, take the algebra of matrices, and we'll consider classical representation. But what is a corresponding quantum algebra? This is an algebra usually denoted by M of n. This is symmetric algebra for R star. This is consists of polynomial functions on the space of matrices. It is generated by linear functions Aij. It can be defined in this way, so the value on the matrix T is just an entry of this matrix. And because the space of matrices is an algebra, this structure of algebra gives the structure of coalgebra on RS star, and we obtain a quantum algebra. And matrix algebra acts linearly on the n-dimensional space as on column vectors from the left and row vectors from the right. And we obtain representation of corresponding algebras of the algebra of matrices and of the opposite algebra. This is algebra with opposite multiplication. And representation space is V. And these representations are given by multiplicative matrices. Rho is given by the matrix M with entries Aij and rho transposed. And this is just a notation. But convenient because it's given by the multiplicative matrix transposed to M. And these matrices define quantum representations, which I denote omega and omega transposed. On the quadratic, these are representations on the quadratic algebra of this algebra of polynomials on V. And omega is quantum representation of M of n, and omega transposed is the quantum representation of M of co-opposite algebra. This is algebra with co-opposite multiplications. We should swap here in terms of factors. Yeah. Now we can deform this matrix. For example, this matrix representation we deform. Here we deform this algebra. We deform this. No, actually here we deform this B, this algebra, matrix algebra, and we deform representation itself. But for simplicity, I will consider only two-dimensional case. So in two-dimensional case, it will be an algebra generated by 4 variables A, B, C, and D with these commutation relations. So without Q, we have just commutativity of all generators, and here we have Q commutativity and also these relations. and co-multiplications and co-unit have the same form, 26. They are not deformed. And the quantum representation space will be Q-plane. This is a algebra defined by two commuting, quadratic algebra defined by two Q-commuting variables. And Manin proved that if Q square is not minus 1, then these commutational relations are equivalent to the requirement that both matrices M and its transposed are AQ Manin matrices. This is Manin matrices for this quadratic algebra. And these two matrices are multiplicative, so they define quantum representations. So we deformed here, we deformed plane, obtained quantum plane, matrix algebra, obtained quantum matrix algebra, and we deformed representation. And we also have the corresponding quantum representation for right action. And in terms of coactions, we can write this representation, quantum representation, in this form. And that Manin proposition means that this quantum algebra is the push out in the categorical sum.
Can you recall what is the definition of MQ2?
MQ2? This relations 29, 30.
So is this somehow somewhat some universal UBV or something? Or not?
No, it's
This one, again, your discussion of universal algebra.
no, it's not, because universal means that we have condition for Manin matrices. So universal is this and this relations. So relations 29, just 29, is the definition
of the universal.
Yeah.
And now you add more conditions, right?
Yes. That means that, and all these conditions is equivalent that M and N
So
transposed is Manin. More conditions. Because
in universal case, only M and AQ Manin, right?
so that algebra is not this is not deformation of matrix algebra. And this is deformation of matrix algebra.
No.
If you put Q equal to 1, we obtain just here we have from here we have 0, so we obtain commutativity of all entries.
I mean, this is there a map from universal to this MQ?
Yes.
So universal is
That's
this
this.
algebra minus.
Yes, this is universal. So this is map.
I see. So universal they are mapped there, right?
Yeah.
And what is T? This is tensor algebra.
Yes, tensor algebra of just this space.
Okay.
So we can interpret the quantum matrix algebra, and the same for the general N, not just for N equal to 2.
So it seems that MQ2 is actually universal algebra which gives both omega Q and omega Q transposed. If you want to get a universal algebra which will give two matrices, not just omega Q, but omega Q and omega Q transposed, we actually need to add this this square, right?
Yes, yes.
Okay. Okay.
So we can interpret this algebra via quantum representations.
Okay.
And so
how much more slides do you have? Just let me ask one question, which seems to be really
slides
important.
maybe 3 slides.
Oh, three.
Ah,
more
4.
3 more slides. Okay.
3 slides and the end. No, 4 slides.
Okay.
Yeah.
We have 3 more slides. Okay, just because we are running out of time, and
Okay.
there is something I really want to see.
So if we want to consider classical presentation of groups, we need how we can do it. We need the notion of quantum group, so homogeneity of a quantum monoid. So this is a bialgebra H. So bialgebra is not graded, so this is not quantum algebra. But we can construct a quantum algebra from this bialgebra. We tensor it with a polynomial algebra of one variable, and we obtain just algebra where H is in each component. And we obtain quantum algebra.
I thought the quantum monoid should be quadratic. It need not be quadratic, right?
Any graded.
Any graded, okay.
Yes. So that's the point. If we consider only quadratic, we cannot do this. So for quantum groups, it doesn't work in this.
Okay.
If we take all the graded, or at least some of them, so we can consider quantum representations of quantum groups
Okay.
and quantum monoids.
So quantum monoid is just any bialgebra, not necessarily graded.
Yes. Yes. And by definition, the quantum representation of quantum monoid, we can just take quantum representation of this corresponding quantum algebra. And quantum representations of H on some fixed quadratic algebra for the idempotent B, these quantum representations in one-to-one correspondence with multiplicative B-minus matrices over the bialgebra H. The condition of degree 1 is not needed because it's automatically, because here for k equal 1 we have H here.
So again, I'm just a little bit confused with the definitions, with the definitions you give. You have bialgebra H.
Yes.
It has co-multiplication and co-unit.
Yes.
Then you tensor it with the k of u and obtain some new algebra.
Yes.
Which is graded again, which is
Right.
now graded.
And the delta and epsilon induces the corresponding delta and epsilon on
With respect to this Marian product.
Yes.
Delta and epsilon should be treated in Marian product.
Yeah.
Okay.
That's why we take k of u, not just k.
And you call this quantum representation. So this is quantum algebra, quantum bialgebra.
No, quantum algebra.
Oh, I mean quantum algebra in sense of dual to coalgebra. Okay, yeah, I see. It's a little bit confusing. Okay, then go on.
So they can be described by multiplicative B-minus matrices over the bialgebra H.
Okay.
And a classical representation can be considered as quantum in this way. So we take classical representation of an affine algebraic group, G, or affine algebraic monoid. It has this form. We take this functions rho here, they form a matrix, and since this is a homomorphism, matrix M should be multiplicative over the bialgebra of functions. So this matrix defines corresponding quantum representation in this sense.
Okay.
And so Yangian example, if it's interesting, or like I omit.
Precisely what I was waiting.
Okay, okay. So let us take a so-called rational matrix, R matrix.
So it could be written
Yeah.
Here we go.
Okay. So consider this R matrix. Z is a formal parameter, formal variable, and Pn is permutation operator of 2n dimensional vector spaces. So Yangian is an algebra. So usually it's defined over some field C. Well, we can define it on any field, at least of characteristic 0. And K will be some another field later. So I denoted by C. So we can think this is a field of complex numbers. So it's generated by infinitely many generators. R is, we have infinitely many R and finitely many INJ. And we take a matrix with which we define in terms of entries. We define it as formal series. So this is an element of this algebra, and this algebra is defined by some computational relations between these entries, and in compact way it can be written in this matrix form, where T is this matrix. This is definition of the Yangian of GLN. And Yangian is a Hopf algebra with this structure. And Chervov and Falke found a Manin matrix from this Yangian. So we take this matrix and shift operator. So this is operator which shifts the argument of functions. So shift operator and Z doesn't come in. And we have many matrix over such ring. To interpret it as quantum representations, we need not exactly this Manin matrix, but we need to extend Yangian by a new generator tone with this relation. So we define this extension by this relation. This, as by algebra, the extended Yangian will be by algebra with this multiplication and co-unit. We denote it in this way. Then we need to extend the fields here. So we need to consider everything over this field. This is a field of infinite Laurent series, so we have infinitely many negative powers and finitely many positive powers. And by field extension, we obtain this extended algebra. So we extended it by tau and by field extension as well. So let it be denoted by H. And H is by algebra over the field K. Then the product of T of Z by tau is a multiplicative Manin matrix over the bialgebra H. No, the reason is the same as for that matrix. But here Z doesn't commute with shift operator. And here tau commute with Z. Tau doesn't commute with generators TR, IJ. That's the difference. So we obtain a minor matrix, and this matrix is multiplicative. So we obtain quantum representation of this extended Yan-Yan on the polynomial algebra. Yeah, and the same can be done for Yan-Yans for orthogonal symplectic case. And this is the end. So as further directions, we can consider super case. We can generalize this theory in terms of enriched categories. We can generalize it to AB Manin matrices. And if we want to consider infinite dimensional case, we need to consider some topology of some type on the vector spaces on the algebras. So it is also interesting to consider, instead of field K, some an arbitrary ring, and to generalize projective representation to quantum case, we need to consider more general graded algebras. Not all the general algebras, but some non-quadratic algebras. Thank you very much for your attention.
Okay, thank you. It was interesting, but yeah, it's a pity we are coming in so late. It will be okay. I think it's almost no time for questions. So, but probably somebody can.
Could you please return to
very
the
short
theorem
question.
of Cherbock and Falk?
Falky.
Is this?
Yeah.
No, it's just a clear statement that.
So if we take here Z to 1, we obtain renormalized antisymmetrizer. So if Z minus 1 equal to 1, then here we have shift, here we have antisymmetrizer here. So, and it will be not equivalent to the condition that this is Manin, but from here it follows that this is Manin matrix.
Wait, I just want to understand. I just want to understand what means the product. You take a product of a Manin matrix, T of Z, and from a shift operator.
No, Manin matrix is the product. So
No,
this is a
this is Manin matrix.
T is this Lux matrix for Yang-Yan.
I understand that the claim is that this is a Manin matrix, but I
Yes.
want to understand where you take this product.
Here.
in which,
So
you just
No, it's very conditionally, so Z and shift operator doesn't commute.
Yeah, I understand. I understand, but the only
They do not commute, but they something. They almost commute, right? Not almost.
With shift,
They
yes.
shift, right?
No,
Well, I don't
if
like this
you
this looks like the commutation relation. ED minus
Right.
Z. It should be. It's just reaction, it's not commutation. Yeah, this commutation relation should look like this. And that's precisely what you have for tau. The only difference is that tau commutes with Z and your
Yes.
this operator doesn't commute with Z. So tau commutes with Z but doesn't commute with the matrix. Interesting. So can you, just one question from me. Can you actually reconstruct, so this Yangian, it has evaluation map from there is an evaluation map from Yangian to universal envelope algebra, right? You just take the generator Tijr and send it to the coefficient of the power of the generator matrix, right?
Yeah. So obtain again the main matrix.
Yeah, but you obtain a main matrix in universal envelope in this way.
Yes.
But what does tau go to? Is there some artificial operator? Can you give some geometrical algebraic interpretation of the tau?
Tau. So there is so there is Haroshkin paper about central extension of double of this Yang for n equal 2. So, and he has element D. So tau is something like this.
About the universal envelope algebra. When you evaluate the Yangian
Yes.
into the universal envelope algebra, what happens to tau? Tau is an operator on generators, right? The tau is an operator on generators. It changes the coefficients. It changes the indices somehow, right?
So
can you write down, for instance, tau of Tij of R? Tij R. So Tij R is an element there. Can you write down how it commutes with tau, with your tau? Yeah, we have this generator, and we have this new generated tau.
No,
Tau commutes with Z, but does something messy
Yeah, okay.
to the generator. Can you write down this formula? Sorry.
it's not easy.
But we have this.
Yes.
You can send me the formula later. Read this.
I didn't. Sorry.
So can you send it to me then?
Okay, I will send.
Please don't forget. I'm really interested in this. I have some very.
This is
strange
in archive. Yeah.
Okay. Can you give reference then?
Okay.
And what was the main object of this paper by Shivov and Falkin?
This
Mining matrices and applications.
Sasha, this should be enough.
Huh?
Sasha, this is enough, definitely. Just find some metrics. Some minor metrics is definitely enough.
I mean, this is the only theorem of that paper.
It might not be the only, there should be examples probably. But
Yeah, that is why I'm asking.
No,
I mean,
it should be
what is the main content of this?
I don't know.
So, do you want what is Talalaev's?
Yeah, but probably it's an application to Talalaev's
Yeah.
construction.
So Talalaev take this matrix and no, you can insert here H here. You can insert H here here also, and you can take limit h to 0, you obtain Godin model in this case. And if you take characteristic polynomial for this matrix, so you obtain integrals of motion.
Actually, we can do this not only for the characteristic polynomial, we can do this as far as I can understand with the traces as well. Traces, you take traces of tau, take trace of tz times tz minus 1 and so on, and it will also be commutative elements, also commutative algebra. That's what I can understand. Okay, separate discussion. Okay, thank you very much. It was very interesting. I'm really waiting for the reference. It promised to say
okay.
this reference. Okay, so the next time, you said that you can make this talk.
Yeah.
Okay, so next time I should have a talk by
Okay.
I think so. And maybe also Eric Shen as will prepare something. I hope. Okay, thank you. Большое спасибо.
Пожалуйста.
Можно отключить, я думаю, уже трансляцию.
Я не знаю как.
Микрофон, все